So welcome students, and in this video we are going to talk about limit cycles and periodic solutions. Okay, so before I start introducing what exactly do I mean by limit cycle, let me just tell you, let me just give you an example to show exactly what I mean. So first of all, example. Okay, so let's look at a non-linear differential system. So now, since see here, we are basically not really interested in linear systems anymore. We are basically doing the non-linear part of that. Okay, so let's look at this system given by x1 prime is equals to minus x2 plus x1 1 minus x1 square minus x2 square. Is it okay? And x2 prime will be given by x1 plus x2 1 minus x1 square minus x2 square. Okay, so this is what sort of equation? This is a nonlinear equation, as you can see. Okay, and of course what we want to do is we are trying to find out how the trajectories of the solutions look like. That's the idea. Okay, so basically we want to find out if there what sort of solution does this problem admits and what are the properties of the solutions. Okay, let's just look at that. Okay, now how do you solve this problem? See, this is a very particular type of nonlinear equations which is actually easy to solve. Okay, since here this term is there, x1 square plus x2 square term is there, that actually gives you the idea that we can introduce a polar coordinate here, r theta, right? So here introducing the polar coordinate, how do we do it? We are writing x1 equals to r cosine theta and x2 equals to r sine theta. Okay, we'll do it like this. Now if we do that, then we use chain rule, right? So what we do is this, let's say d dx of r squared. Let's just calculate this thing. What is it? D dx of r squared. Okay, so this is nothing but 2r dr dx. Okay, which is nothing but see 2r dr dx. Okay, I can write it as 2x1 dx1 dx. I mean, if you want, you can write it as x, or maybe I can write it as t. That will be, I think it is better. Otherwise you may get confused between x1 and, so let us write it this way. Okay, so t plus 2x2 dx2 by dt. Is it okay? This is what you are going to get. Now if we just calculate it, so this is chain rule, right? This is chain rule. Okay, now if we just calculate this thing, I hope you know, you understand what I'm doing it here, what I did here, right? Okay, so now see this 2x1 du1 dx1, I can just write down that x1 prime, right? So which is 2x1 minus x2 plus x1 1 minus x1 square minus x2 square. I will just put everything together, right? Plus 2x2 and then again dx2 by dt, which is essentially this. Let us put it there, x1 plus x2 1 minus x1 square minus x2 square. Is it okay? So I put everything together. Now if you just calculate this thing, see this and this particular term is gone. So essentially 2x1 square and 2x2 square, that's what I have. So basically it is 2 x1 square plus x2 square. This is what I have. And then we also have 2 x1 square plus x2 square and then the square of that. That's what we have, right? And then that will actually give you 2 r square 1 minus r square. Is it okay? That's what we have. Now you see, and so basically hence what do we have? Dr by dt is nothing but 2r 1 minus r square. Yes, if we put everything together, that's what we are going to get. Yes, and similarly, please check this part. Similarly, we also have d theta by dt is nothing but 1. Okay, so you have to check this part. So now if we look at this system, see this system, this is the system which we started out with, right? So this system 1 is equivalent to this system, right? dr by dt is equals to r1 minus r square, and d theta by dt is 1. This is the system. Now we can easily solve this system, right? One can easily solve this system. Why? Because this is basically, you see, this is independent. The first equation is independent of theta, and the second equation is independent of r. So we can separately solve this problem, right? One can solve it. One can solve the above and obtain the general solution, and the general solution will be given like this. Solution is r of t is nothing but some r naught. Okay, so r naught is basically r evaluated at the point 0. Okay, and then r naught square plus 1 minus r naught square e power minus 2t times half. Okay, I did not calculate it. You guys can easily check this part. Please again do it. And then theta of t, if we want, we can just calculate it, is t plus theta 0. Okay, so what is r, where r0 is given by r at the point 0, and theta 0 is nothing but this. Yeah. Okay, so see, this is in terms of r and theta. So therefore the general solution of 1, the general solution of 1, how does it look like in terms of x1 and x2 is, okay, x1 of t, x2 of t, that's your solution, right? Let me write it this way. See, this is nothing but r naught by r naught square, okay, plus 1 minus r naught square e power minus 2t whole power half. Okay, and then cosine t plus theta 0. Yes, so that is the first, and the second part is again similar, this thing, r naught by r naught square plus 1 minus r naught square e to the power minus t to the power half, and then I have sine of t plus theta naught. Yeah, that's what we have. Now you see this trajectory. Yeah, if you look at this trajectory carefully, so let's just write it 2. Okay, see, 2 is a family, right? It's basically a family of curve. It's a sorry, this 2 is basically a curve, right? Okay, and the trajectory of the curve, if you want to put it precisely, so essentially 2 defines the trajectory of the particle, okay, obeying 1. Yes, in x1 x2 plane. What do I mean by this? You see, what I meant is, see, this system is nothing but basically a particle which is moving in the x1 x2 plane, right? Based on the parameter t, that is, yes. Then so the rule is this one. Okay, so x1 prime and x2 prime is given by this, and the trajectory is given by 2. Is it okay? Now you see, we are going to analyze this thing. Okay, so let's look at this. So first of all, A, see, if r0 equals to 1, let's just put this part there. See, if r0 equals to 1, this becomes 0, this becomes 0. Okay, that is why I am taking r is equals to 1, and then r naught square whole power half is r naught, and r naught gets cancelled out, so basically this becomes cosine and this becomes sine. Okay, so if r naught equals to 1, then the trajectory x1 of t and x2 of t will look like cosine of x plus, sorry, not x, t plus theta 0 and sine of t plus theta 0. Is it okay? Yes, and you do realize that this is nothing but solution, a periodic solution of period 2 pi. Okay, so this is a periodic solution of period 2 pi. Is it okay? So basically what we have is in this particular case, so basically if we are choosing this condition that r at the point 0 is 1, under that condition this is what we are going to get. You are going to get a periodic solution of period 2 pi. And how is the card moving? It is moving in the anti-clockwise direction, right? You're just looking at it. Okay, so the trajectory is traced in the anti-clockwise direction. Okay, this is just for our information, we don't need it that much, but that's the thing, anti-clockwise direction. Okay, now let's look at this condition. If r naught is not equals to 1, maybe, yeah, then the trajectories are definitely not closed. Why not closed? Because you see that exponential part is there, right? This exponential part is that it cannot be closed. Yes. Okay, so what's happening here is this. Let's just see the trajectories defined by 2 are not closed, right? And so if they are not closed, of course they are not going to be a periodic solution, right? See, if it is not closed, it cannot come back to itself, right? So basically it cannot be a periodic solution. Okay, and since this e power minus 2t, this part is there, you do realize that basically this will be something like a spiral kind of thing. It has to be, right? Okay, so that's just the graph of this particular locus. Okay, so they are not closed, and in fact are spirals, I hope it is clear to you what I meant by this. Okay, so see, depending on the initial data, either the solution becomes a periodic solution, okay, of certain period, whatever, in this case it is 2 pi, or it is actually not closed and it becomes a spiral. Okay, now you see, if r naught is strictly less than 1, okay, see, if r naught is strictly less than 1 minus r naught square, that should so I mean, you know, this should be less than this is a positive term, right? If r naught is strictly less than 1, so this term becomes r naught by r naught square plus some positive times e power minus 2t whole power half. Okay, what you can see, say from here is, then r naught is less than 1, the trajectories okay, are spirals which lying inside the circle. Which circle? The earlier one, this circle. Let's just call this as a 3. 1, 2, 3. Okay, because of this coefficient, you can check that this actually will you can check that this will be less than 1, this will be less than 1. Okay, so hence this will be a spiral, of course, but they will always, the spiral will lie inside the circle. Is it okay? Yeah. Now the thing is, as t tends to, and you do realize that as t tends to infinity, you see this is a spiral, right? And we are saying that since this term, okay, and this term is bounded by 1 essentially, so this lies within the circle. Yes, and as t tends to infinity, e power minus t, you see, as t tends to infinity, e to the power t goes to infinity, 2t goes to infinity, right? So e to the power minus 2t goes to 0, so this goes to 0, so this will be again, you see, this actually is actually merging towards the circle now. Yes, okay. So what is happening here is this, see, that as t tends to infinity, okay, the spiders approach this circle. Which circle? The 3, this circle, this is the 3 circle, this, the trajectory given by 3, this is, while now what happens when t tends to minus infinity, they approach, while t tends to minus infinity, see, as t tends to minus infinity, what happens, this becomes infinity, right? Yeah, so the whole thing goes to 0, so basically this actually goes towards 0 0, which is nothing but the critical point of the system. Okay, so as t tends to infinity, they approach okay, the only critical point, okay, 0 0 of 1. Is it okay? See, by looking at the this equation, you can do realize that 0 0 is the only critical point. If there is a critical point, it has to be 0 0, right? Okay, so the 0 0 is the only critical point, and this particular thing, this actually goes to 0 0, right? Okay, as t tends to minus infinity. Okay, that's what I'm saying. That so basically what is happening is this: as t tends to infinity, they approach the circle, while as t tends to minus infinity, they approach the only critical point. Okay, now again, you see, this is for r naught less than 1. Now if r naught is greater than 1, then what happens? Okay, the trajectories, now you see, the trajectories are not inside the circle but outside the circle. Okay, if r naught, the trajectories, okay, what am I saying? Yeah, so in this case they are lying inside the circle, right? So r naught is greater than 1, then the coefficient will be greater than 1, right? So these coefficients, these ones, okay. And what happens is, in that case, it will lie outside the circle. Okay, the trajectories lies outside the circle. I hope this is clear. Okay, now you can actually check, so please check this one. This is easy to do. Check that the outer trajectories, okay, also approach okay, this circle. Which circle? This circle, the only circle I have, this given by 3, trajectory given by 3. Okay, this circle, as t tends to infinity. Okay, while this also you can check. Okay, as t tends to half log 1 minus 1 by r naught square. Okay, both x1 and x2 blows up, so basically becomes infinite. Is it okay? So what we did here is this: if r naught is greater than 1, so if you are starting from initial data such that r at the point 0 is greater than 1, then the trajectories, they will lie outside the circle. Okay, and as t tends to infinity, they will actually approach that circle. Okay, while as t tends to this finite number, whatever the number is, both x1 and x2, they becomes infinite. Is it okay? Yeah. So you see, what happens is this: what does this basically say, this whole analysis? Let me just summarize. So summarize, let me do it in maybe red. So summary, what is the summary? So you see this, the differential system 1, okay, the system 1, okay, shows that the trajectory that the trajectories of a nonlinear system, okay, may, this is one of the examples, huh? So may spiral into a simple closed curve, okay. See, the thing is, what it is saying is this is may. So basically it's not like it always has to be, but it may happen that the trajectories may spiral into a simple closed curve, okay, right. So these from this particular example, we have a definition. The definition is due to Poincare, okay. So this is called the definition of limit cycle, okay, definition, okay, and I'm still using red because this is very important, okay. So this is the definition of something called a limit cycle, okay, due to the great Poincare. I hope all of you know who Poincare is, right? Poincare, okay, right, okay. So what's the definition? The definition says that a closed trajectory okay, of the differential system of the x prime equals to f of x, okay, which is approached okay, spirally from either inside or outside by a non-closed trajectory, okay. So in our earlier cases, what is that non-closed trajectory? The spirals, huh? So basically what it is saying is this: we are looking at a closed trajectory, yeah. So think of it as a circle, let's just say, huh? It can be anything, but let's just think of it as a circle. Now basically what we are doing is we are approaching it spirally from inside or outside by a non-closed trajectory. So you know, let's say this circle is there and we are approaching it like this, okay, we are approaching it like this from the inside, or we are approaching it like this from the outside, okay. And see, this is non-closed, it is not closed, huh? Okay. So this is the thing. Now the thing is by a non-closed trajectory, okay. What am I saying? It's approached spirally from either inside or outside by a non-closed trajectory, okay, of one either as t tends to infinity or as t tends to minus infinity is called a limit cycle of 1. I hope the definition is clear. See, in our earlier cases, what is happening is this, basically this is a solution of this problem, right? A particular solution. And what is happening is this solution, there is like the two different trajectories which are non-closed trajectories, yeah. And as t tends to infinity and t tends to minus infinity, what is happening is it is actually approached either. So in this case, the earlier case, depending on the initial data, that is, okay, it is either approached from the inside or it is approached from the outside, right? Okay. And those, so basically the closed trajectory, okay, which is basically approached, that closed trajectory is called a limit cycle, Please don't get confused with the non-closed trajectory. Okay, so the closed trajectory which is being approached, that is called the limit cycle of one. Is it okay? So in this case, what is the limit cycle? This is the limit cycle. Okay, the closed trajectory which is being approached, that is the limit cycle. Is it okay? Huh? Okay, so that's the definition of limit cycle. Now the thing is this, we have a very important theorem. This theorem is due to, again maybe I can go back. This theorem is actually guarantees that whether there exists a limit cycle or not. Okay, so let me give you the theorem. This is basically necessary and sufficient condition for the existence of limit cycle. Is it okay? Now see, I want you to emphasize one thing. See here, it may not look much, okay, but the thing is, nonlinear systems are notoriously difficult to study. Yeah, these are the only few tools which we have available in our disposal which we can use. Yes, and to be very frank with you, most of the nonlinear dynamic systems, if you want to study those sort of systems, nonlinear dynamical systems which you can get either from biological systems or like physical systems, I mean, there is like a lot of applications of this particular theorem, yeah, which I am going to explain now. So this theorem is called the Poincare-Bendixson theorem. This is called the Poincare-Bendixson theorem. Okay, again, this is one of the cornerstone results of dynamical systems. Okay, nonlinear dynamical systems. So how do I put it? This is part of a nonlinear dynamical systems. Okay, now see, the thing is, the definition, I am going to write down the exact statement of the theorem. The proof of this theorem is actually not I mean, within the scope of this course. If you want, you can of course look it up in the book Lawrence Barco. Okay, but the thing is, the proof is extremely complicated. It's not like a very straightforward proof. Okay, so let me give you the statement, and for our course the statement itself is enough. So suppose that a solution x of t, okay, which is given by x1 of t, x2 of t, okay, of the system 1, or maybe I can write down the system x prime equals to f of x. So essentially we are looking at a nonlinear system. Yes, okay. So what we are saying is this: let's say that there is a solution xt of this system, okay, and it remains bounded. Okay, it remains in a bounded region, region of x1 x2 plane, region of x1 x2 plane. Is it okay? Which contains no critical points. Is it okay? Yeah, of x prime equals to f of x. So basically what we are saying is this: if by some we don't know how, but what it is saying is this: if you can somehow how do I put it, capture the solution. Yeah, if you have a solution of this system, and if you can somehow capture the solution in a region, yes, which does not have any critical points of the system, yes, then it's a beautiful theorem. its trajectory, must spiral into a simple closed curve. A simple closed curve. Is it okay? So what it is saying is this: if you can trap a solution in a region which doesn't have any critical point, that is important, yes, then this trajectory, okay, will actually spiral into a simple closed curve. Okay, this is important now, which itself is a trajectory, okay, of a periodic solution of x prime equals to f of x. So basically you see, if you can show that there is a solution which gets trapped inside a region, okay, bounded region of course, which doesn't have any critical points, yes, then that solution, okay, the trajectory of that solution will spiral into a simple closed curve. Okay, that is fine, but the important part is this: it will actually spiral into the simple closed curve is actually the trajectory of a periodic solution. Okay, so basically this theorem also tells you that if there is a, under such circumstances, it is possible to find a periodic solutions also. So basically, if you want to find out a periodic solution, you can use this and you get your required result. Okay, so you can also use this theorem to find periodic solution. Is it okay? Yeah. Right. So that is the thing. This is why it is called the existence of limit cycle, because that is what we are trying to find out, right? The limit cycle. Okay. So let me give you a particular example of how to calculate this particular using this particular theorem. Okay. So let's look at this example. So let's say consider the differential equation y double prime plus 2y square plus 3y prime square minus 1 times y prime plus y equals to 0. Okay, so this is ODE is there. Now what I am doing is we are converting it into a system. So if you do that, let me do it this way. This is equivalent to x1 prime equals to x2 and x2 prime equals to minus x1, okay, plus 1 minus 2 x1 square minus 3 x2 square, yes, and then y prime, right? So basically x2. Okay, right. So this is the system. Now you see, the thing is, let's say that for any given solution, let's just call this system as star. Okay, for any solution, okay, of course it is given, huh? We know that there is a solution xt which is given by x1 of t and x2 of t, okay, of star. We note that, you see, this is very easy to see, that d dt, okay, of x1 square t plus x2 square t is nothing but 2 x1 of t x1 prime of t plus 2 x2 of t x2 prime of t. Is it okay? Yes. Now if we put the values of x1 prime and x2 prime, this is what we are going to get. Here we are going to get 2 1 minus 2 x1 square of t minus 3 x2 square of t times x2 square of t. Yeah, I hope the calculation is correct. Yeah, 2x1 x2 plus 2x2 x1. Yeah, so okay, yeah, fine. Yeah. Yes, I hope this is correct. Now you see the thing is this. See, the thing is we want to find out that whether there is a limit cycle or not. So basically we want to find out without explicitly solving this problem, or of course I mean you see we are not trying to solve this problem, right? We are just trying to find out whether there is a pediatric solution for this problem or not. Yes. So by this Poincare-Bendixson theorem, what we need to do is we need to find a solution which is trapped inside a bounded region which doesn't have any critical points. That's what we need to do. Okay. See, now what happens is this. Since this is one way of doing it, yes, what I'm going to do is when we will be talking about the assignment, you can of course solve the assignment, but I will also for this particular this thing week, I will also give you another small idea, okay, while discussing the assignment of how to solve this problem using another trick. Okay, that is also a easy trick, but this is another way. So basically two ways you will learn. So now see, since 1 minus, now look at this particular expression, 1 minus 2 x1 square t minus 3 x2 square t. Okay, this term, this is positive, right? If x1 square plus x2 square is less than 1 by 3, that you can easily see, right? And this is negative if x1 square plus x2 square is greater than half. Yes, this is not very difficult to see. You check this part. Okay, see, 3x1 square plus 3x2 square minus 1 is less than 0. So basically this has to be positive, right? Okay, right. So you see the thing is in this case, so we have, see, x1 x2 10, x1 x2 10, right? Yeah, x1 plus x2 square less than 1 by 3, x1 plus x2 square, you see, let's say this is x1 square plus x2 square equals to half, and this is x1 square plus x2 square equals to 1/3. Yes, so the thing is this, in this case what is happening is this, x1 square plus x2 square greater than 1/3 but less than half is this area. You see this annular region. Is it okay? Now the thing is this, since ddt of x1 square plus x2 square is positive, x2 square is positive and this part is positive, in where x1 square plus x2 square is less than 1 by 3, and it is negative if x1 square plus x2 square greater than half. Okay, what we can say is this, the function x1 square t plus x2 square t, okay, is increasing yeah, when x1 square plus x2 square is less than 1 by 3. Yeah, because you see this is positive, right? This function ddt of this particular function will be positive, so basically the function is increasing, yeah, in that region, x1 square plus x2 square less than 1 by 3, and decreasing in the region x1 square plus x2 square greater than half. Is it okay? Yeah, so you see this differential equation, let's say the start, the system, yeah, this has a trajectory, right? The given solution, let's say x of t, and this trajectory, what is happening is this, if you move along the trajectory, okay, x1 square plus x2 square will be increasing. Yeah, so basically you see this trajectory x of t has two components, x1 of t and x2 of t. Okay, so x1 square plus x2 square is nothing but norm of xt square. If you look at it carefully, right? So what it is saying is this: the norm is increasing where in this region where x1 square plus x2 square is less than 1 by 3. So in this case, in this region, you see the, where is it? Yeah, in this region, less than 1 by 3, this region, the norm is increasing, right? Okay, so if your trajectory is in this area, so if it is going towards the boundary, it is increasing, right? And it is decreasing in x1 square plus x2 square greater than half. Okay, greater than half means here. So if your trajectory is in this position, the norm x1 square plus x2 square, okay, the absolute value of that particular thing is actually decreasing. You understand? So what that says is, if a trajectory starts here, let's say anywhere here in the annulus, okay, huh, then it will remain in the annulus. Is it okay? Of course it has to be. See, it cannot go this way, right? Because it is decreasing in this way, and it cannot go, I mean, it cannot cross this and go here, because in this case it is increasing, right? Okay, so you do realize that once it starts here, it has to be contained in this whole area. Is it okay? Yeah. So that's what I'm trying to say here, that we are trapping this trajectory. Basically, if a trajectory is starting here inside this annular region, then it remains there for all time t. Yeah, that's what. So this is the whole idea. See, here also you do realize that the critical point, see there, here the critical point is 0 0. The critical point is 0 0, right? And the thing is, this annular, where we are saying that the trajectory, if it starts in this annular region, okay, it will remain in this annular region. This annular region does not contain 0 0. Okay, you understand what we are, where we are going with this? So basically what we are, let me write it down. So let's say if x of t starts in the annular region, starts in the annular region, okay, what is the region? x1 square plus x2 square lies between 1 by 3 and half. Okay, at t equals to, let's say, 0, okay, it will remain in the annulus for all time, right? Annulus for all time. Okay, if you are not convinced, pause the video again and think about what I told you. Okay, the norm of xt essentially. Okay, so if it starts in the annular region, it remains in the annular region, and since the annular region does not contain any critical point, then the Poincare-Bendixson theorem, what does it say? So therefore the Poincare-Bendixson theorem implies that the trajectory of this solution, which solution? The x of t which we started out with, of this solution. See, we started out with this solution, right? X of t. Yeah. Now, of this solution must spiral into a simple closed curve. Right? What is the guarantee? That is the guarantee what Poincare-Bendixson says, that if you have a trajectory which you can, trap inside a region which does not contain critical point, then that has to spiral into a simple closed curve. And what is so special about this simple closed curve? This actually is the solution of this problem. Okay, which itself is a non-trivial solution. Of course, non-trivial. Okay, was a non-trivial periodic solution of one. I hope this is clear to you. Okay, and so what does it guarantee? It guarantees that this system, see, by looking at this system, how can you say that there is a periodic solution? But we use Poincare benediction, and we said that, if we have a solution like this, then of course it has to spiral to a non-negative periodic solution. Okay, so basically that system has a periodic solution. Okay, so that's how you could talk about, use Poincare benediction. Okay, now the thing is this, but is there a guarantee that there are always close trajectories? You understand? See here, there it is saying that it actually spirals into a periodic solution. So basically, there is a close trajectory which solves the equation here. But the thing is there a guarantee that there will always be a close trajectory? So in particular, that is there a guarantee that there may not be any limit cycles? Can you do something like this? So basically, now let me put it again in red. So we want to see that if we can find a condition under which we can guarantee the non-existence of limit cycles. Limit cycle. Is it okay? Non-existence of limit cycle. Okay, so to this end, what we are going to do, we are going to prove something called not prove. Okay, maybe we can prove why. It's not very difficult to see. So it's called a Bendixson theorem. It's the same Bendixson like the Poincare Bendixson. Bendixson theorem. So what does the theorem say? It's very easy theorem. So it says that if del f1 by del maybe x1 of x1 x2 plus del f2 by del x2 of x1 x2, okay, if that has the same sign, okay, throughout the domain D, then the differential system x1 prime equals to f of x1 prime equals, write it this way, x prime equals to f of x. Okay, and what is f of x? We write it like this: f1 of x1 x2 and f2 of x1 x2. Is it okay? Yeah, f1 f2 x prime equals to f of x has no close trajectories, okay, in the domain D. So basically what we are saying is this very easy theorem. You have x prime equals to f of x. F is a vector field from R2 to R2, let's say. Now you see, you just look at so basically f is basically f1 and f2, right? Now you just look at del f1 with respect to del x1 and look at del f2 with respect to del x2. Add those two functions up, and if they do not change sign throughout the domain D, then we have that there is no close trajectory. Very simple. Okay. Now this proof will do because this is a very easy proof. Okay, and what we are going to do is this: let's say that there is some region in D, okay, let's say, which is bounded by a closed curve C. Okay, so let S be a region in this region in D, okay, which is bounded by a closed curve C. See here, it is saying it doesn't have any closed trajectory. So let's just start with the closed trajectory. If there is a closed trajectory, you see there is a closed trajectory, so there will be a region which is bounded inside. Okay, let's just call this region as this. That's the thing. Okay, now the thing is this. Now what we have is this. We can use the famous Green's theorem. Okay, Green's theorem. So what does Green's theorem say? If we do that, it basically says the integral over a closed curve, okay, f1 x1 x2 dx2 minus f2 of x1 x2. I have to be very careful, there are too many indices here, one second, dx1. Okay, so this is nothing but double integral over the area integral over s del f1 x1 x2 by del x1 plus del f2 of x1 x2 by del x2. Okay, this is what dx1 dx2. This is just Green's theorem. There is nothing, I am not writing anything special here. Okay, so by Green's theorem, this is what we have, right? Now you see, let x of t, which is nothing but x1 of t and x2 of t, x1 of t and x2 of t, okay, be the solution of x prime equals to f of x, okay, whose trajectory okay is a closed curve C in D, is a closed curve C in the domain D. Is it okay? And W be the period of the solution I hope this is clear, huh? So basically we are starting out with the solution, okay, closed solution essentially. So basically a closed curve, huh? Which is actually a closed trajectory, which actually solves the problem, huh? Let's start with that. Then from the Green's theorem, what do we have? From this theorem, what we have is this. See, integral. Okay, maybe I can copy part of it, huh? Copy, so paste, huh? So we have this particular thing equals to integral 0 to w, that's the period, right? So now I have g1 of u1 of, sorry, not f1 of u1 x1 of t x2 of t dx2 by dt minus f2 of x1 of t x2 of t. I am not doing anything, I am just writing this thing, I am just writing this part. So this double integral I am just evaluating it and writing it here, okay. It is dx2 by dt dx, right? If we just evaluate it, that's what we are going to get, and then this is nothing but this is 0, right? This is 0, okay. So therefore what do we have is this, you see this particular thing, yeah, if it just does not change sign, okay, then double integral of this particular expression, okay, this is, so basically you see, if this expression is 0, this expression is equals to this double integral, so that is part is 0, right? Okay, so therefore double integral of s del f1 by del x1 plus del f2 by del x2 dx1 dx2 equals to 0. Is it okay? Yes. And therefore what do we have is, if this is 0, you see this does not change sign, so it is either positive or negative, okay. But see, the thing is it is 0, okay, if it has to change sign, right? So you understand, if it is either positive or negative, then the double integral of this particular thing cannot be 0. Is it okay? So that's a contradiction. So a contradiction. I hope it is clear. This does not change sign, so either it is positive or negative. If it is positive also, then also the double integral of a positive quantity has to be positive. If it is negative, then also same thing. Yeah? And you have to understand f1 and f2 are continuous functions. So basically neighborhood property actually guarantees that if it is positive, it has to be positive in a neighborhood. Okay, so it is actually positive. Okay, so now we finish this video with a small example of how to use this Poincare, this Bendixson theorem. Okay, very simple example. So let's say x1 prime equals to x1 times x1 square plus x2 square minus 2 x1 minus 3 minus x2, and x2 prime equals to x2 x1 square plus x2 square minus 2x1 minus 3 plus x1, sorry, x1, yes, maybe I can write it here, x1. Is it okay? Now the thing is this, for this system, you see, this is f1 and this is f2 of x1 x2 of x1 x2. Now you can check that del f1 by del x1 plus del f2 by del x2, in this case, what is it? This is nothing but 4 x1 square plus 4 x2 square minus 6 x1 minus 6. Okay, so please check this part, okay. Now this particular thing you can write it like this: 4 x1 minus 3 by 4 square plus x2 square minus 33 by 16. Okay, so you see, if you have if you have a circle, okay, with radius 3 by 4 0, okay, so if you have a circle with radius 3 by 4 0, okay, and the the center 3 by 4 0, and that's this is the center, and the radius is 34 by 16 root over this. Okay, that's your radius. If you have a circle like this, in this circle, within this circle, inside the circle, okay, this particular thing is basically negative. Is it okay? And then what happens is that the Poincare, the Bendixson theorem guarantees that there is no closed curve in this disk. Okay, so within this disk, okay, there is no closed curve of this system. Okay, so in this region we can guarantee that within this region there is no closed curve. I hope you understand the region. The region is this particular thing, this particular thing. Okay, inside the region there is no closed curve. Is it okay? So with this I am going to end this video.